Good evening, everyone. Welcome to this session of the training program, which is run by the South African Mathematics Foundation for senior students in training for Olympiad type examinations and programs. At the outset, I want to apologize for last week. I didn't pitch. It's one of those very rare occasions when I don't do my duty. I got confused with the dates and therefore was not able to be there. I must apologize for any inconvenience caused. Okay, today we are going to continue with session 7. Last time we did session 6. Today's program is largely on geometry. Now, geometry is usually a bugbear amongst learners, but amongst the students like you who really love mathematics, geometry can be a very exciting and an enjoyable part of the mathematics program. It is one of those areas, one of those few areas in the school curriculum where you have to really think and use logic and be creative. Now, talking about creativity, in most of the problems that you encounter in school, you are given the diagram. In fact, in all, you are given the diagram and you are asked certain questions which lead to the answers. In Olympiad type problems, you are given very few clues and only sometimes you are given the diagrams. And in many cases, you can't solve the problem as it stands. You might have to perform a construction, a new line or a new part of the geometry, which will help you to solve the problem. You've seen constructions. If you have been looking at theorems, and all the theorems, in fact, without any exception, every theorem has a construction. And that is why they are relegated to the realm of theorems, because they require a little bit more insight to solve those problems. But here in problem solving and in Olympiad problems, you are expected often to perform constructions. Usually it takes a long time before you get to finding the construction which works. But when it does, then there is a great rejoicing on the part of the person who is solving, because it is an exercise of creation. It gives you immense satisfaction. All right, now with those few background words, we have quite a few problems to tackle today, and I will be going somewhat briskly. And hopefully, if you don't understand anything, you can go back to the recording. All right, so let's go to today's session 7. So it's supposed to be done on the 15th of September, but we are one lesson short. And at some point or the other, that lesson will be advertised. That was supposed to be last week's, but we're going to postpone that some other time. All right, so let's now get to the first problem. Okay, I'm going to continue with some of the problems which I didn't do. I'm not sure, I think this may be the only one that we didn't complete at the last lesson. So quickly, let's just go through that. This particular problem, which was in session 6, it says the following: given any 4 points on a plane such that no 3 are on the same straight line, what is the maximum number of acute angle triangles that possible with the vertices amongst these given points? All right, so you got 4 points, and you are expected to draw triangles with those 4 points. Now, if you got 4 points, you can normally draw a quadrilateral. Mm. Okay, so when you draw a quadrilateral like this, you can actually, if you join the diagonals, remember the question says with vertices amongst these given points. So we want to draw triangles with vertices with only at these chosen points. So like for instance, this triangle is one of them. There are actually 4 triangles which you can draw. In each case, you omit one point and you get 3 other points, and those 3 points create one unique triangle. So, but you can omit 1 point in 4 different ways because there are 4 points. Each time you omit a point, you get a triangle, and those will be, so there are a maximum of 4 triangles which you can draw. And the question is, what is the maximum number of acute angle triangles you can draw? Right? When you try to do this, you will see that, like for instance, the triangle with this, with that vertex removed, gives you this triangle here. You can see it's looking like obtuse. And even if you remove this vertex that I'm pointing to, you'll get these 3 points. That also looks as if it's obtuse. So there are, in my diagram, I've got 2 obtuse angle triangles, and the other 2 are the ones above and below this diagonal, and those look as if they're acute. So in this triangle here, in this setup, I've got 2 acute angle triangles and 2 obtuse angle triangles. And the question is, what is the maximum number you can draw? Now, it's quite possible to draw one with 3 acute angles. All right, I'm going to try to do that. I'm not sure whether I can do it. I know if I draw a kite, I can draw a kite. Now, why is this okay? And here, I can try to draw a slightly acute angle. Let's go down and here, make that acute also. And now you can see I've got that triangle, and the up and the bottom triangles. But this triangle here will be obtuse, the one at the bottom. So you can make this acute, that acute, and you join this, you have 3 acute angle triangles. All right, so you can draw 3, but they asked you what is the maximum number. So the next question is, can we draw 4 acute angle triangles? Is it possible to get all these triangles to be acute angles? I'm going to try to address that problem. It's not quite obvious. So what I've done here so far is I said we can draw 3 acute angle triangles. You can try it. You can construct a kite which has got 3 acute angles. But it's not possible to have 4. Now what is the reason for that? Okay, I'm going to explain to you, actually give you a proof why it's not possible. So here's a figure here. Suppose all 4 triangles are acute angles. Now, okay, so in other words, okay, so if all 4 triangles are acute angles, then A is in one of the triangles, B is in another, C is another, and D is another, right? So, so all these angles will then be acute. A, B, C, D are all acute. Now, if that is the case, That means all of them are less than 90 degrees. A, B, C, and D, all less than 90 degrees. So when you add the whole four, each one is less than 90 degrees. They're all acute. So if you add the whole four, you're going to get less than 360 degrees. All right. But you will see that these four angles, they actually add up to 360 degrees because those are the angles of a quadrilateral. The sum of the angles of a quadrilateral is 360. And now, if all of these are acute, then you're going to have a problem because you'll have 360 is less than 360. So what we have done is we have assumed that it is possible to have four triangles, and we came to a contradiction. We proved that 360 is less than 360, which is impossible. So in other words, the assumption that I made that we can draw four triangles has a flaw in it, because that allows us to lead, it takes us to an impossible ending. So therefore, it is not possible to do it. All right, so let's just go on to the next one. The second problem that I'm going to discuss is the following. All right, it says the following. Question, the square ABCD has length 6 units. M is the midpoint of AB. Okay, let's just put that. M is, oh, the sides are 6 units. So all the sides are 6. If M is the midpoint, then it means that each of them is 3 there, as I've shown. Okay, there's M. And P is a variable point. P is somewhere here, but we don't know where it is. It's a variable point. Now they say find the smallest value of dP, there's dP, plus PM. So you want to add these two line segments, and you want to know what is the smallest possible value. Now, as P moves, you will see that you have different sums, dP plus PM. Right? When P hits B, then you can actually calculate what dP plus PM is. Right? Because then you got the diagonal of the square, which you can calculate. But you have these numbers change. The sum will change as P changes. The sum of dP and PM varies. Now they want to know what is the smallest possible value. Okay, now a little bit of thought will say that, you see, if dP plus PM, we can't calculate this thing as it is, but we're going to use the fact that the straight line is the shortest distance between 2 points, and that will give me the smallest value. Now, how do you use that? What we are going to do is the following. Now watch. I'm going to take this PM and I'm going to put it on the other side. So it'll be easier to see what dP plus PM is. Now, how do I put it on the other side? What I do is, I'll just extend this thing. When I say on the other side, I'll reflect it across BC, as if BC is a mirror and MP is translated on the other side. And that is the same as extending MB by another 3 units and joining these two. See? Then what happens is, if I extend this by another 3 units, I've got 90 degrees here. And if this is another 3 units, these two triangles then become congruent because you got 90, 90, 3, 3, and this is common. So these two triangles are exactly the same. So in other words, PM is now equal to this one here. So now we want to find the smallest possible value of dP plus Pm, and let's call this one here n. So it's the same as dP. This dP plus Pm in my figure is the same as dP plus Pn, because by this construction, I extended this thing by another 3 units. I got this. Now, when is dP plus Pn as small as possible? Now remember, P is running along this line, right? It'll be smallest. This is a broken line, you can say, right? So it'll be the smallest when dPn is a straight line. Okay, that you have to try to understand that. So if I join this, in other words, I'm saying that P is at this point here. See, P is running all over here. When P is in this position, right, then dPn is a straight line. Right? And dP plus Pm will be the same as dP plus Pn, and that's dn. Now, dn will be definitely the smallest possible sum, because there is the triangle inequality, which we have discussed before, that the sum of two sides of a triangle is always greater than the third side. So you got dP plus Pn is always bigger than dn, right? If dP and n form a triangle. All right, so therefore this will be the shortest line, dn. So what is dn equal to? The answer to this question is dn. Now dn can be calculated because dn now is a straight line. So you got a right angle triangle. dn squared, right, is equal to an squared plus ad squared, because you got a right angle triangle. This is a square. So by Pythagoras, we can actually calculate dn. You see, because dn we know is 9 by construction. I'm sorry, an. So this is 9 squared, and ad is 6. It's given that it's 6. And this is 117. So dn is actually equal to the square root of 117. And that is the smallest possible value of dP plus Pm. This is quite a common way of doing things. When you try to look for the smallest sum, try to put those points in a straight line. And when it's in a straight line, then you use the fact that the straight line is the shortest distance between 2 points, or which is the same as saying that the sum of two sides of a triangle is always greater than the third side. Okay, so that takes care of that problem. And we go on to the next problem. Here you see again, you got a rather simple little figure, not very complicated. That is why I like problem solving. You don't have a complex problems and so on. The deep questions are in the simple diagrams. That's where the deep questions are. Not always, but very often. Now here you got this is an acute angle triangle. BC is equal to AB plus 1. Now I'm going to give symbols to these. I don't like to use BC and all. Let's call BC. Now, the traditional way of naming sides in a triangle is you name it you name it as the same as the opposite angle. So this will be small a, and this will be small b. Let me get back to my black. This will be small b, it's opposite angle b, and opposite angle c is c. That's the traditional way of doing it. You don't have to do it like that, but then you keep track of what's going on. Because in triangle geometry, very often an angle and the side opposite it act as partners, right? Very important that a small angle A and the side opposite, which we call little a, are partners. We'll explain later on what do you mean by partners, all right? But bear in mind that when you have a side, you also sort of think of it together with the angle opposite it. Okay, now if you name them like that, then BC is C. BC, oh no, wait a minute. BC is A, sorry. BC is A equals AB plus 1. AB is C plus 1. So you got a nice, neat little equation here. Okay, that's finished. Then you got AC. What is AC? B. AC is B. BC plus 1. Again, it's A plus 1. Right. So you've got some relationships between the sides. If you give names to these sides, you'll 5, 6, and 7 or something like that, then you'll be able to see exactly how to construct this triangle. Okay. For instance, if A is 5, then B is 6. And if A is 5, then C is 4. Then you have a 4, 5, 6 triangle. All right? But we are not given any particular value for A. But despite that, the question is, what is CD minus BD? CD minus BD. Now that's interesting. That means it's always the same thing. You'll get the same answer no matter what you choose A, B, and C to be. Or you choose A to be. Once you choose A, then B and C are automatically chosen. So regardless of the size of this A, the CD minus BD is apparently the same. That's very interesting. That's one of the beautiful things about geometry. It's very surprising statements. Now, let's call this. Okay, I'm going to call CD minus BD. Now, this is the question. Now, I said these problem solving require a lot of intuition and ingenuity. Now, one of the ways of doing this is, you see, you've got right angle triangles here. So evidently, Pythagoras will have to be kicking in somewhere, right? I mean, Pythagoras, you've got square terms. And here, there's no square term. But you do know that CD plus AD, we know that's equal to A, you see, CD plus AD. And a very useful algebraic fact is that CD minus BD into CD plus BD, you get the squares which I'm looking for. CD squared minus BD squared. A squared minus B squared is A minus B into A plus B, or otherwise A minus B into A plus B is A squared minus B squared. Right, so I've got my square in here, and this thing here, CD plus BD, is little a. Right, so now you have a nice equation, and I might be able to calculate this question mark. But the trick is to multiply this by CD plus BD. That comes with a little bit of experience. So you've seen it now today, so perhaps next time you see this, you will be able to use that trick to try to get squares in. Now, what is CD squared? CD squared is one of the sides of this, the square of the side of this right triangle. Let's call this H, because H is the height of the triangle. So CD squared is B squared minus H squared, plus or minus BD squared is C squared minus H squared. This is Pythagoras. And minus H squared plus H squared cancels when you remove the brackets. You land with B squared minus C squared. So that is B minus C into B plus C. All right? Now we can substitute for B in this. So what is B minus C into B plus C? Now B is equal to A plus 1. Let's make everything in terms of A now, because according to these equations here, C is equal to A minus 1, and B is equal to A plus 1, and of course A is equal to A. So you can replace all these symbols with only A's. So let me do that, so I have only one symbol here. So B is equal to A plus 1 minus C. C is A minus 1. There's a minus in front of the brackets. I'm going to make it minus A plus 1. And here I've got A, B is equal to A plus 1 again. But this time it's plus A plus 1. Now here I've got 2. These A's cancel off. And there's something funny going on here. I think I made a mistake here somewhere. No, I haven't made a mistake. Can't understand. Oh yeah. Oh no. Okay. Now B plus C is, sorry, B plus C is A plus 1 plus A minus 1. Sorry. All right. Yeah, I'm supposed to substitute A minus 1 into this. I got mixed up with this because the sign changed. Now, when you simplify this, you get, let's just go this way. You get 2. And here you got the 1 minus 1 cancelled, then you have 2A. So you get 4A. But now you've got C minus D, C minus CD minus BD times A is equal to 4 times A. So the A's cancel off, and lo and behold, you can calculate CD minus BD. The A's cancel because you got A on this side, 4A on this side, and you get 4 CD minus BD. Okay, so that solves that problem. Very nice algebraic problems, a lot of algebra in this. But geometry, algebra, trigonometry, and all that, they all can be used interchangeably to solve all kinds of problems. Algebra doesn't remain by itself. Geometry doesn't remain by itself. I often use algebraic symbols to simplify geometry into algebra because I can calculate, see, all this is algebra, to calculate geometrical problems. Okay, so let's get on to the next one. Next problem, question 3. The diagram shows quadrilateral PQRS. Okay, we can see it's a quadrilateral with PQ parallel to SR. Okay, so you've got PQ, this is PQ, and it's parallel to SR. Oh, so you have a trapezium, right? You have a trapezium. Now, some sides are given. In fact, the diagram has got the sides. PQ is equal to 5, 4, and 7. Okay, so those are translated into the diagram. The two triangles are similar. Oh, no, this is interesting. They are similar. In other words, they have the same angles. These two triangles have got the same angles. Now, using this information, they tell you if PQRS is not a parallelogram, what is its perimeter? So in other words, you need to know what the sum of all the 4 sides are. What is 4 plus 5 plus that plus that? Right? So that's the question. And they give you some information. They say their triangles are similar and it's not a parallelogram. All right, now because they are similar, I'm going to just put symbols here. I'll put a dot and I'll put a curl and I'll put say a cross here in the one triangle. So in this other triangle, I've also got a dot, curl, and a cross. Okay, but we don't know where they are. Now, for one thing, we know that this line, since this line is parallel, you got a Z angle here. So this dot here is equal to this one here. These are alternate angles. So at least now you've got one of those angles equal to this angle here. Now you've got two other angles to fill in. So you can have a cross here or a curl here. All right. Now I'm going to just start off by saying, suppose I have a cross here. I either have a cross or a curl. But suppose I have a cross here. Now, if you look at this now, what you've got is this cross is coming down, going like this, and the cross here. If these two angles are the same, if this is a cross, then it will mean that these PS and QR are parallel, right? So that will mean that this pair of opposite sides are also parallel, like that one, which will make this into a parallelogram, right? So I'm going to say this again. If this was a cross, you can conclude that this entire figure is a parallelogram, which is a contradiction because it says it's not a parallelogram. So it means that this is not a cross. Now that means only one thing. If that is not a cross, then it has to be a curve. The only two possibilities, right? So this has to be a curve, and this will be a cross. So now you got two similar triangles, and we know exactly which angles are which. All right. Now, when you have similar triangles, I think we've said this before, the sides are in proportion. The ratios of those sides are the same. But you have to take the sides which correspond, the corresponding sides in proportion. So suppose I look at the top triangle. You can put in triangle PQS. Now, when I name this triangle PQS, I will name the other triangle in the same way. P is a curl, right? So I'll put the Q in front, right? Because the curl is here, and at the Q in the top triangle is the dot, and in the bottom triangle, the S is at the dot, and you have, and then finally QS, of course, you're left with QSR. And so we're looking at these two triangles. Now, these triangles are similar, right? So you can write down the ratios. Now, it's very easy to write down the ratios if you name this thing correctly, the way I've done. At the equal angles, you will name those points at the right spot. When you do that, I don't even have to look at the diagram. I can just write down the three ratios. I'll put PQ first second over QS first second. Right. Second third is QS on the left-hand side, and second third on the right-hand side is SR. And the only thing that remains is first third, which is PS, over QR. See? PS over QR. And now, those are the three ratios. You can get it without even looking at the diagram. Now we can make the substitutions. Because PS is equal to 4. So I'm just going to make that 4. We got PQ is equal to 5. This PQ is here. I'll make that 5. And then what else have we got? We got QS is 7. So let me, where is QS? QS is 7 here. Oh, I'm sorry. What happened here? PQ. Oh, this is 7 here. QS is 7 here as well. QS occurs twice. Didn't realize that. So there was a 7 here, and also there was a 7 here. QS occurs twice because QS is in both triangles, you see? So it occurs twice. And now you only got two unknowns. You got SR and QR, and you can calculate that. See, so from this equation, there's 5/7 here. So in this equation, there's only one unknown. You can calculate SR, and SR is immediately 49/5. And then you've also got these two equations here like that, from which you can calculate QR. 5/7 is equal to 4/QR. So it's 4 times 7 is 28/5. So there it is. You've got SR and QR. This is SR. So you got that, 4 and 5, and you can calculate the perimeter. And if I recall correctly, the answer is 122/5. And we're not going to waste our time with simple addition in this problem solving class. All right, you've got the numbers there. Okay, let's now get on to the next problem. See, the last problem was involving similar triangles. Right? So it's a good example on similar triangles. We've got a good introduction to it. The two triangles have got the same angles, and the sides are in proportion. That's why we wrote down the three ratios. Right? First, second over first, second, second, third over second, third, first, third over first, third. And then after that, all you have to do is to just make the substitutions, and you can get straight to the answers. All right, now let's have a look at this next problem here. Two vertical sticks in the ground have length 2 meters and 3 meters. The top of each stick is joined to the bottom of the other. So you got this top of this stick is joined to the bottom of the other stick, and the top of this stick is joined to the bottom, right, by means of two strings. The strings meet at a point P. What is the height of P above the ground? So in other words, I have to draw the vertical line, right? To draw the height, I have to draw the vertical line like that. And I want to know what is this height? H. When I saw this problem the first time, I was quite intrigued because it doesn't say how far these sticks are apart. It asks you for the height as though it doesn't matter. And I thought that's quite weird. Because if you got a stick here and you got this other stick extremely far away, 1 kilometer away, you would expect this height to be very close to the ground. Right? You would expect this height to change as you move the sticks apart. But the remarkable thing in this, the mathematics tells you, no guys, the heights always remain the same, no matter how far these sticks are apart. Right? All right, so how do you go around this? In the first place, these sticks are vertical. They say they're vertical, so there's a 90 degrees here. So now you've got a figure here, you got this triangle, and you got this is parallel. Now, whenever you see a setup like that, immediately you got two similar triangles. Okay? You must always be wary of a triangle where you got one line parallel to another line. Because then this triangle here has got the same angles as the large triangle, because these are corresponding angles, you see. If you've got parallel lines, then these angles are equal, they're corresponding angles, and these angles are also equal. And then you see the small triangle has got this one here, curl dot cross, and the large triangle also got curl dot cross. They are similar, and therefore the sides are in the same proportion. See? So that's very nice. So here I've got in this triangle here, if you want to call it A, let me get back to my black. We call it A, B, C, D, maybe E, right? If you look at this triangle ACD, you got PE is parallel to that. Now, we don't know what these lengths are. Let's just call it A and B. All right, so you've got PE is parallel to that. Therefore, this small guy here is similar to the large guy, right? They got the same angles. And when you look at the ratios, the ratio H is opposite this little dot. And in the large triangle, which is similar to it, you got 2. It's given that this is 2. And then I'm going to only use these. This is B is in the small triangle, opposite, let's call this curl. And in the large triangle, the side opposite curl is this big one, A plus B. So you have this equation, H over 2 is equal to B over A plus B. I need to calculate this H, you see. But I've got too many unknowns. I've got B and A plus B, right, which is a little bit problematical. Okay, now I can do the same thing using the 3. Right, how do I do that? I could have done this. Now, it's still 90 degrees. So now in this triangle here, I've got this line and these 2 lines are parallel. Right? In fact, you have it's like this. This is parallel to all 3. And this time now, in this large triangle, right, where the side is 3, I've got this exactly the same thing. I've got H there over 3, but this time the small triangle is on this side. It's going to be A over A plus B. Right? A is opposite, A and A plus B are opposite the same angle. All right, now I've got 3 unknowns and 2 equations, but I need to, how do I do this? A quick glance of this will see that, wait a minute, when I add these 2, it's A plus B over A plus B. Bingo. B plus A over A plus B. And A plus B, it commits suicide, and both of them are gone. So now you have a single equation in H, and we can calculate H. Right? One equation in one unknown, multiply by 6 right throughout. I don't like fractions. If I multiply this by 6, I got 3H. If I multiply this by 6, I got 2H. I multiply this by 6, 6 times 1. So H is equal to 6 over 5, which is 1,2 meters. Very beautiful problem. That this height here, it is quite independent of how far apart these poles are placed. A very remarkable and curious conclusion. Okay, so let's get on to the next problem. See, we are doing a lot of these problems all on similar triangles. And similar triangles is a very important part of your metric syllabus. So I'm doing something which is very, very useful for you. A lot of questions in geometry in the final grade 12 paper deal with similar triangles. So I'm doing some interesting things with similar triangles here. So you're going to benefit quite a bit even when your schoolwork. All right. Now, there's another important thing about similar triangles regarding the areas. Let me just let's make a point here. Suppose I've got 2 triangles that are similar. That means they've got the same angles. Now, a very important thing is the following. Suppose you call this A and B, make it A, B, and then suppose this is, say, X and Y, right? Now, these angles are the same, and the other angles also. Now, the ratios, X over A is equal to Y over B. X over A is equal to Y over B. Now, if we regard X over A as the, what shall I say, the scale factor. In other words, this thing over that is how much larger it is. So if we call it, if you call this K, then X over A is equal to K. In other words, this X is some number K times A. So this is some number times this. And if you look at this, you also got Y is equal to K times B. And Y is the same number times B. That's what ratio is all about. Y is some number times B, and X is the same number times A. And this is very useful because when you're doing similar triangles, instead of having two unknowns here, I can eliminate those two unknowns by saying, I'm going to call this the scale factor times A, and Y is a scale factor times B. Y is KB. So now I've just got A, B, and K, you see. I don't have A, B, X, and Y. In mathematics, we try very hard to try to reduce the unknowns. And this is a nice trick to reduce the unknowns, right? If you just use the scale factor. Now, the other nice thing about this is that it now tells you the areas. If the sides are, if this side is K times this area, how much bigger is it than that? Okay. So if you call this small a small and A large, right? The small area, there is a formula in trigonometry which you're going to use. The area of a triangle is half the product of two sides, half AB, times the sine of the angle between them, the included angle. I'm just going to call it dot here. So you've got the area of this triangle is half AB times sine of dot. And the area of this triangle, the large triangle, is a half KA times KB times sine of dot. The same dot occurs here. So now we've got two formulae here. And if you take the ratios of these, interestingly, I want to know how much larger is this than that. So I'll put this over that to see how much larger. If you take this, you'll see the halves cancel, the A's cancel, the B's cancel, even the sines cancel, and you have K squared, which is so nice. So the ratio, this one here is K squared times that. The sides are K times the sides of this, but the area is K squared, the same scale factor. You have to square it to multiply it by this to get this area. All right, I just needed to give you that background. I went through that quite hurriedly, but it is one of those things that you use in school. And I don't think they even prove it. They just simply tell you that the one area is the scale factor squared times the other area. And they don't tell you where it came from. And if you ask them, they will say, God told me. All right, so we want to solve this problem now, bearing in mind all these things. What I'm going to do is, you see, these two triangles here, I want to know what the area of ABZ is. That's the question. You know that is 30, you know there's 50, these lines are parallel. And now if they are parallel, then alternate angles are equal, and these corresponding angles are equal. I'm sorry, these are also alternate angles. And this triangle here has got the same angles. These two triangles have got the same things. So if you call this A, and if you call this B, and as I told you earlier on, this is KA. Oh, wait a minute. Yeah, the A. A is opposite curl in this top triangle, and opposite curl in this is this one. So I have to call that KA. See, A corresponds to curl in the small triangle, and what corresponds to curl in the large triangle is this. So if this is A, this is KA. I told you earlier on that these comes in pairs. This is what we are saying now when I say A corresponds to that. So likewise, this is KB. See? All right, so because these two triangles are similar, now what is K? K is actually equal to the third ratio. K is equal to, you have to multiply this over this is K, that over that is K. So it has to be, the third ratio is 54 over 30. That over that. So K, we know exactly what the value of K is. 6 goes into both of these. So it's 6 times 9 over 6 times 5. So K is 9 over 5. Okay, so we know exactly what these ratios, what the stretch factor is, right? It's 1 comma 8, 9 over 5. Now we need to know what the area of this triangle is. Now, the area of this triangle ABZ is half base times height. We already got the base, but it's times the height. Now, we haven't got the height. So let's yeah, I thought there may be a shortcut to this, but I can't see it straight away. Okay, so let's draw the height. You're going to use another color for height. I'm going to go right through, right? So that is the height there. So you'll notice um, oh, the lengths are 56. Oh man, I was wondering why I can't solve this problem. We've got another piece of information here. I, I made the big mistake of not reading this thing. I'm just looking at the diagram. AC and BD, the lengths are both equal to 56. They are equal in lengths. Okay, so AC is equal to BD. Now, AC is K plus KA. That's AC. And BD is B plus KB. All right, K is a common factor here. So it's K into A plus 1 equals B into K plus 1. K plus K. No, the A plus K, sorry. Guys, I think I'm getting too old. Okay, let's just get A plus KA equals B plus. So A is a common factor here on this side, and on the other side, B is a common factor. So if I take out A, 1 plus K, and B, 1 plus K. So happily, the 1 plus K is cancelled. So A is equal to B. See? Right, so you got A equals B, and I need to find the area of this triangle. Okay, so I really don't need this height here. I'm going to, I know now that A equals B, which is very, very useful because now this triangle here is an isosceles triangle. And the area of an isosceles triangle is quite easy to calculate. So I'm going to redraw this isosceles triangle so that I get a good picture of what's going on. But I'm going to squeeze it in here. Let me take this thing out. In fact, it seems that I didn't need to know what the stretch factor was. The K is cancelled. So if I redraw this triangle here, ABZ, I'll get something like this. And it's an isosceles triangle. So these are equal. Okay, and this is 30. So you got an isosceles triangle where these two are equal. And uh, what are they equal to? Do we know? Oh, yeah, we know that K is, oh, yeah. It's 56, right? Okay, so we know that this is actually equal to 56. A plus KA, we haven't used that fact, is 56. So therefore, we can calculate A then, because you got A into 1 plus K is 56. Right, so that gives you A equals B, but it also tells you, I calculated K earlier on. It was 1 plus 9 over 5, if I remember correctly, is equal to 56. So K is 9 over 5. And so when I substitute K equals this, then I have only one unknown, so I can calculate A. This is 14 over 5. So A times 14 over 5 is equal to 56. So A is 56 times 5 over 14. And happily, 14 goes exactly into 56. So A is 20. So you got, that is 20. That is 20. So you have the three sides of this isosceles triangle. And we should be able to work out the area. Should we? Do you know how to work out the area of a triangle like this? Right. Now here's something. Maybe you didn't know how to find the area. The area of a triangle, if the sides are given, it's not in your syllabus. Right? There is a law called Heron's formula, but that is not in your syllabus, where you can calculate the area of a triangle if you know the three sides. Right? Those of you who want to research it, you can look at Heron's formula, very interesting formula, which gives you the area of a triangle if the three sides are given. No, we are not going to use Heron's formula here, because in an isosceles triangle, you don't need Heron's formula. You can work it out directly, because all you do is split it in two. I've said this before and I say it again. When you got an isosceles triangle, always break it into two equal parts. And then in that case, what happens is that the two triangles are exactly the same. And therefore, the bottom part, which is 30, is split into two equal parts. And so this becomes 15 and 15. And these are two right angle triangles. That's what happens with isosceles triangles. You can split them into two right angle triangles. Now you can calculate the height, right? And you can calculate the area. Okay, so I think you get area is equal to 75 root 7. You can check it out. Right. The height is from Pythagoras, you can do it. And the area is half base times height. So the half base is 15 times the height, which you can calculate, and that's the answer. And I'm not going to waste my time doing that because we've got other things to do. We don't have much time. Okay, so let's get on to the next problem, which is question 6. Question 6. So consider triangle ABC. Oh, no diagram is given here. Right. I told you that this is one of the things that they do. They don't give you a diagram. So in this particular case, I'm going to use black. Right. So you got a triangle ABC. When you're drawing a triangle, try not to make it look isosceles or equilateral or something like that. Try to make it a general triangle with 3 different angles. Otherwise, you start having a bias. You look at your own diagram and say, ah, this is isosceles, when it's not supposed to be isosceles because you drew it like that. Okay, so you got triangle ABC. M is a point on line AB. So you got a point M. MN is parallel to BC. So I'm going to draw a line through M, which is parallel to BC, MN. Right. If MN bisects the area of triangle ABC, so ABC, MN bisects the area, it means that this area here is equal to half the area of ABC. Right? Now, 2 things feature here, which we've already discussed in this session itself. Namely, that if you've got a parallel line, then you've got similar triangles, which is one. And secondly, these 2 triangles are similar. This baby triangle is similar to its mother, the big one. Right? So you got 2 similar triangles, and of course, lots of things happen. But here you're talking about areas, and we know that the area is equal to AM over MB. So we need to work out AM over AB. So in other words, AM over AB. Now this is precisely the ratio AM over AB of these 2 similar triangles. It's actually the AM is smaller, so it can't be a stretch factor, but it's that. Let's call this K. So AM over AB. If you call it K, then we know that I said this before, the triangle area of triangle AMN over the area of triangle ABC is equal to the K factor squared. It's this over this. It's the same as AM over AB squared. That's a K, which I spoke about earlier on. The ratio of the sides. So that is K. AM over AB is K squared. But we also know that AM, this thing bisects the area. So it's given that this area is half the area of the whole thing. So suddenly we have this ratio is known, right? The ratio of this triangle to its mother is a half. So that immediately tells you what K is. So K squared is a half. So K is 1 over square root of 2. And that is what we needed to find. K is 1 over square root of 2. So this ratio AM is to AB. If you want to answer the question, it's 1 is to root 2. AM over AB is the same as AM. AM is to AB is the same as AM over AB. Right? I hope you know that. x is to y is the same as x over y ratio. Okay, so here, because we knew that the area is the square and yeah, and what I said about the scale factor, then we can solve this problem very quickly. So, so we have said everything that really needs to be said about similar triangles, and I hope you go into your grade 12, that's where they do similar triangles, very confidently, um, understanding all the intricacies about similar triangles. Okay, so the next question is this one. Okay. Oh, what happened here? My, oh, all right. Oh, the picture is too big. All right, doesn't matter. We really don't need too much in this picture. Now, the question 7 says the following. AB is a diameter of a circle with center M. So this AB is a diameter and M is the center. Now, remember, if M is the center, then all the radii are the same. There are lots of radii here. Well, at least I got 1 and 2. Immediately, you must know that MC is the same as MA. All right. So an AB is a diameter, and some of you would know that a diameter, the interesting thing about a diameter is that it subtends a right angle at the circumference, but I don't think I will need that. So, but if you do know that it subtends the right angle at the circumference, then you'll be able to solve this problem using that fact. But since there are some grade 10s here, we are not going to use that fact. Um, we'll try to do it using grade 10 geometry. All right. Chord CD is parallel. Oh, all right. So CD is parallel. Oh, I've got it. I've got it in this larger diagram here. CD is parallel, right? And MC meets AD at the point E and all that. Okay. So eventually you've got all the information that you need. That this line is parallel to this. And the problem, oh, you haven't got all the information. You got also that AC equals EC. AC, I'm going to look at this picture here, is equal to EC. So these two are equal. So you got a small isosceles triangle sitting here, right? Now, the question is calculate angle CAM, this angle here. What is CAM? Now, this is a very curious problem because not a single angle is given. In most geometry problems, they will give you a couple of angles and you expect to use those angles to calculate the unknown angle. But here, not a single angle is given, and they ask you to calculate what is CAM in degrees. So it's quite a curious problem, an interesting problem. But obviously, there is one angle given here, and that is the 90 degrees, right? Because AB subtends 90 degrees. But I'm not going to use that. All right, what I'm going to do is the following. I'm going to start naming these angles. In terms of a single angle. Now, I want you to see what I've done here. I've performed a little construction here. You see, I only had two radii, MC and MA, and that's an isosceles triangle here. We're also given that this one here is another isosceles triangle. But there are lots of other isosceles triangles here. If I join MD, because then you got a new line here, and this triangle there becomes isosceles, that one becomes isosceles. So, so the more isosceles triangle you've got, the more information you've got, so the quicker you can get to your solution. So I've actually joined MD. It's not obvious, but I try to justify it. All right, and then we'll try to give a name to one of them. You see, I know I've got alternate angles here. So if I give a name to this x here, right, then the alternate angle here will be x, because these two lines are parallel. Right? Now this is x here, and you got an isosceles triangle here, because MA is the same as MD, and this is a base angle, so this becomes x. Right. So now, so it turns out that DA bisects this angle. But now you got this entire angle here, which is 2x, and because it's parallel lines, this angle here will also be 2x. These are alternate angles. So this is 2x. You could have done it like that, or you can say that this is the exterior angle of this triangle here. This red line together with that, x plus x is 2x. You could have done it that way as well. Right, but now that this is 2x, but it's the base angle of this triangle here. MD and MC are equal in length, right? Because they are radii. So if that is 2x, this is 2x. And this is what you call diagram chasing, right? Using the information, you keep chasing the diagram until you get more and more information. Now, if this is 2x, now you got another alternate angle here. This is 2x here. So this angle here becomes 2x. Remember, I'm trying to find x. And to get x, if I can get an equation involving x, I've solved it. So I'm still investigating all the information you have got. And this is 2x, this is 2x. And now I got x here and I got 2x here. So in this small triangle here, AEM, I got x and I got 2x. And this, if you add these two, you're going to get the exterior angle. And the exterior angle in this triangle is this one here. This angle here, I might have mentioned the flag theorem. The flag is looking like that. So you got this is x and 2x. So this is 3x. But now we are at the isosceles triangle. This is 3x, so this is also 3x. See? Because these two are equal. It's given. AC equals AC. But now you have that MC is equal to MA because these are radii again. And this angle here is 4x now. Right? It's a base angle. So therefore, this angle here is also 4x. Because that's the other angle in MCA. That's an isosceles triangle. Look, these are not very difficult. You might not be following what I'm saying, but you can easily do it yourself because you must just observe that there are lots of isosceles triangles. So each time you have a single base angle, you can move on. And then you've got parallel lines, so you must just use that fact to get alternate angles are equal and so on and so forth. And now suddenly in this triangle here, I got three angles which will add up to 180. And that's my equation. The small triangle. I got 4x, 3x, and 3x. So 10x is 180. So x is 18. We actually found x, although no other information was given. So x is, because this is 10x, and we are asked to calculate CAM, which is 4x, according to our figure, CAM. And that's 4 times 18, which is 72 degrees. Okay, so this uses only parallel lines, isosceles triangles, and the fact that the radii of a circle are equal. Very, very elementary facts it uses. No major theorems. And we can solve this problem. So it's not a difficult problem, but it's a nice problem. Okay. So let's just get on to the next problem, which is this one. So let's see what this problem is. Uh, all right, okay, I got my picture here. Now, this question is going to be an interesting situation. You got a circle and you got like two rectangles. You can see two rectangles. It says two congruent rectangles. Now, the word congruent is used in outside congruent triangles. Congruent triangles are identical triangles, and congruent rectangles, right, will obviously mean they are identical rectangles, which means they've got the same sides, right? So this rectangle has got the same sides as this one. All right, so that's what's given. The area of a rectangle is 12. So one of these rectangles, the area is 12. So let's call the length and the breadth, call it x and y. So it means that xy is equal to 12. Length and breadth is 12. That's the area. Its perimeter is 14. So the perimeter of this is 2 into length plus breadth. So length plus breadth is 7. So you get xy is equal to 12, and x plus y is 7. You have two equations and two unknowns. Now, if the circumference of the circle is n pi, what is n? Oh, no, it suddenly went onto the circle. Okay. Now, so we need to move, cast our attention to the circle, right? And we need to know the circumference. We know the formula for the circumference. The circumference of a circle is pi times the diameter, or otherwise 2 pi radius, 2 pi r, the same as pi times diameter. So I notice here that this is 90 degrees, right? Which means that this chord subtends an angle of 90 degrees. This chord here. You see, this chord subtends 90 degrees at the circumference. So that chord has to be the diameter. Right? So this is the diameter of the, so I need to calculate the diameter of the circle. So what is this? If I know the diameter, then the circumference is pi times the diameter, right? So, and then, so the n is actually the diameter because the circumference is given as pi times n. So we need to calculate the diameter. Now the diameter is part of a rectangle, of a right angle triangle. Now these triangles are congruent, so it means that this is also x here. The breadth is the same, and this is also y there. Okay, so your diameter, let's call it d. D squared is equal to x squared plus y squared. Now, actually, I wouldn't have done all that. I would have said, look, xy is 12, x plus y is 7. So you can mentally you can see what x and y are, because the product of the two numbers is 12, and the sum of the two numbers is 7. And of course, you can see it must be 3 and 4, right? 3 times 4 is 12, 3 plus 4 is 7. So x and y are 3 and 4, and therefore d squared is 3 squared plus 5 squared, or 4 squared, which is 25. And therefore, d is 5, and the circumference is pi times the diameter. It's 5 times pi. And it's given that the circumference is n pi. So therefore, n is equal to 5. That's the question. What is the value of n? It's given that the circumference is n pi. So by inspection, you can see what this is going to be. All right. Now, in case you are not very happy with that, there is another way of doing this thing, which is a nice, clever way. And I think I've done a problem which is very similar. If you know the sum and if you know the product, then you know the sum of squares, the sum of the squares. Right? And there you would use x plus y squared is equal to x squared plus y squared plus 2xy. Normally the 2xy comes in between, but I'm purposely putting x squared plus y squared because I need to calculate that. And x plus y is 7, so it's 49. X squared plus y squared is what I'm looking for. And 2xy, xy is 12, so 2xy is 24, and therefore x squared plus y squared is 49 minus 24, which is 25. You come back to the same thing, right? Without guessing, you can actually prove that x squared plus y squared is 25. Okay, so let's get on to the next problem. We get to the so in question 9, two tangents are drawn to a circle from a point A. So you can see I've drawn from a point outside to the circle. Okay, now you got some circle problems. Now those who are in grade 10 might have not done circles, but that's just what I'm saying. At some point later, you will come across these facts, and so I'm just giving you a sneak preview into what you can expect. Now, one of the things about circles is the thing about tangents. A very important thing about, not an important thing, but a tangent to a circle, I think you should know that, is a straight line which just touches the circle. From a point outside a circle, you can draw two tangents, exactly two tangents. So you can go like that. If I go like this, it's going to cut it in two places. As I go down and down and down, I come to a point where it just touches it. And that'll be the tangent, right? So from a point outside the circle, you can always draw two tangents. And these tangents are actually equal, right? I'm not going to go and spend too long over it, but I can tell you very quickly why they are equal. To see why they are equal, you actually go to the center of the circle. And from the center, you join the center to the what you call the points of contact, right? When you take a center of a circle and join it to where it's touching, there's a theorem in geometry which says that it's going to be perpendicular. These angles are 90 degrees. It's a very useful theorem, right? That when the radius is always perpendicular to a tangent at the point of contact. Right? Very useful theorem, right? Now, these two are actually equal. Why? Because if you perform one other construction here, if I join this, these two triangles are congruent. Right? These two triangles are congruent because these are radii, you see, from the center of the circle. Now these two triangles, you've got 90 degrees, the radii, and this is common. Right. So you've got the reason for congruency is hypotenuse, side, and angle. It is not included. This is that reason. So if they are congruent, the black lines are now equal. Okay. And that's exactly what I said, that these two tangents are equal in lengths. So you can prove it. It's not very difficult to prove. So bearing in mind that, then you have two tangents are drawn from a circle, which lies outside. They touch the circle at points B and C, as you see, right? A third tangent, there's a third tangent here, right? Intersects AB at P and this. So this is also a tangent. There are three tangents to the circle, right? And they tell you that AB is equal to 20. They give you the length of one of the tangents. AB is equal to 20. And they ask you to find the perimeter of triangle APR. That's asking for quite a lot, right? What's the perimeter of APR? So let's write down what this is. APR. We need to work out AP plus PR plus RA. So we want to know what the perimeter is. We know only AB, right? That's the length of the tangent from A to B. Now PR can be written as PQ plus QR. So you got AP plus PQ plus QR plus RA. Now PQ, from this point outside, I got PQ must be equal to PB. Because the same thing here. I got a point outside and these two tangents are equal. So PQ is the same as PB. And QR is the same as RC for the same reason. So you got AP, that one, plus PB, plus that one, RC, which is that one, and RA. So you got AB and AC added here. But AB and AC are the same because from the point outside, these two tangents are equal. And AB we know is already 20. So this is 2 times 20, which is 40. Right. So you actually can calculate the perimeter of this triangle. Another very interesting fact, it doesn't matter where the Q is, the perimeter is always going to be the twice the distance from A to the tangent. These are all very revealing facts. If you think about it and say, not just how to prove it, but what does it mean, you know? There's some very interesting consequences from all this. All right. Now, look, I'm at the end of this. I'm not going to do the next one, but I'll do the last one. And I also want to discuss your assignment. So if you bear with me, please just remain because I'm going to discuss your assignment. Or maybe I better discuss your assignment first in case some of you want to leave before that. So this is your assignment for today. It carries 20 marks, so it's quite an important assignment. Now, look, the problem is the following. You've got a square, ABCD is a square, right? And I should have said all these things. Anyway, ABCD is a square. I think that's the only thing that is said. And then now that from this point here, a 30-degree angle is drawn to come and hit this point G. It's given that DG is equal to 1. And on the outside, another 30 degrees is drawn to go and meet the extension of this at the point E. And now you got this E is joined to G and C is joined to F. And you got two triangles here, and the problem is to find the shaded area. Now, this turns out to be not a trivial problem. That is why I'm discussing it with you. Those people who did not attend this class would not benefit, but you could share it with them. I don't know how many people attended today's class. Now, if you try to do it like that, you'll find it very hard. In fact, I'm not even sure whether it's possible to actually calculate these two areas, the sum of these two areas. But if you perform a construction, I took a long time to eventually get to this construction. By joining D and B, DB, right? Then this problem can be solved. That is all I'm telling you. The DB, if you join DB, the problem can be solved, right? And just observe that the sum of these two, they look very odd, but the nice thing to do is to add the white triangle to it and subtract it. Then you will get the difference of two triangles. When you add the white triangle, you get the triangle, this large triangle. And so therefore the sum of these two is the large triangle minus this part which has been removed. I mean, once you got that, then you have to find the areas of these two triangles, the removed triangle and the large triangle. And you got right angles and sides and all kinds of things in it. Now you got 30 degrees also. And I think the grade 10s might have a problem with that one because the sine of 30 degrees will feature here. 30 degrees is an important angle. I might have said it before that 30 degrees, in a 30-degree triangle, you can calculate the sides. Right angle triangle, that is. Anyway, you can, the grade 10s can go back and just go and revise that stuff, and you'll be able to calculate all the three sides of that triangle. And then there's a lot of calculations, and eventually you'll get. Please try to write down as much information you can, even if you don't solve the problem. Because the 20 mark consists of a lot of part marks. Each time you calculate something, you'll get some mark for it. So you can get a lot of marks even if you don't solve it, but do all the calculations and show the calculations accurately. If you are saying the two triangles are congruent, then you must explain why. There are congruent triangles in this thing here, so you'll use congruent triangles as well. All right, so that's the assignment problem. And if you want to go, you can go, but I want to do this last problem, which I find one of the most interesting problems. In fact, many people, teachers, they find this quite fascinating, this particular problem, because it's a practical problem. You've got these washers, you call them washers, these steel things with the hole in the middle. Right, now, I'll tell you what the story is. It says that you can balance this washer on a number of rings like this, washer rings, but in such a way that this washer actually touches the ground. These rings are obviously on some table or something like that. They're sitting on some flat surface. And this washer here, the vertical one, is touching the ground. Okay. Now they tell you that, and they give you the inner diameter. That means the circle, the inside circle, what the diameter is, and the outer diameter, the outside circle of these two. The inner diameter is 40. The inner diameter is 40, and the outer diameter is 58. So just remember, those are the two numbers that is given. And also the thickness of these washers, how thick they are, from one edge to the other. It is said that 1 millimeter. So each of the washers are 1 millimeter thick. So you want to know how many are stacked here for this to happen. So you need to know what this height here is. If I know h in millimeters, then I will know how many rings I've got, because each washer is 1 millimeter in thickness. So if this height is h millimeters, it means I've got h rings. So I need to calculate this height. Okay. Now, how do you do this? Using our geometry, right? And this is where it becomes quite fascinating, because what you do is you look at this washer vertically. I'm going to draw it here. Oh God, let me just get my black in. Maybe I better put it in here. So I'm going to draw this vertical. I'm looking at this vertical washer at the face, right? And then this 2 points here, which are on the outside, I'm going to join them. You see, these 2 points, where this thing here touches this top washer, I'm going to just mark this point here. And the other point on the other side also, I'll mark those 2 points. And you will see that when you join these 2 points, it's horizontal, right? Because all these things are on a surface. So this washer is vertical, and the 2 points, they're horizontal, so you can join them. But the interesting thing is that when you join these 2 points, you're going to get the diameter of the inside one. See? That's what I've just drawn here. So this thing here is the diameter, the inner diameter. And we know the inner diameter is 40. So this length here is 40. Right? And you know the diameter of the large circle. Right? It's 58. So now the question is, what is h? H is actually, this part here is actually on the ground, as I told you. So h is this distance from this line here to the ground, right? And that is your h. So I need to calculate that length there. So it's very interesting, because you take this picture here and you make it into a ordinary diagram of geometry, and so the question is, what is h? If you know the diameter is 58. All right. Now this is how you do it. So you have to bring in the circle. As you have to draw there's a lot of constructions involved here. And I have to bring in the center of the circle into view. I need to calculate this height. So let me draw the radius. To get this height, I need to draw this one here. Okay. So I join this point here to the bottom. Right. Now I know that is the radius. It's the radius of this large circle. And the radius of the large circle is 29, because the diameter is 58. Right? So I know this distance here is 29. I need to calculate this. So then it means I need to calculate that one. Because if I know the whole thing is 29. So if I know this, then I know what h is. I just have to subtract it. So how do I do this? Now, the thing about this is that this line here is perpendicular to the floor. This is tangent, you see. So a circle is always tangent to the bottom. So therefore it's perpendicular to this, and this is parallel to this, which means that this must be 90 degrees. See, this line here is parallel to the floor. So 90 degrees. Now you have an interesting theorem in geometry, which says that when you join the center of a circle, you draw perpendicular to a chord. Now that's what I got here. The center is drawn perpendicular to the chord. Then it turns out that that chord is actually bisected. That chord is actually bisected. Because these two triangles are congruent. Huh? These are radii, these are 90 degrees common, they're congruent, so therefore this piece will be the same. So you have got that this chord is bisected, the whole chord is 20, 40, so that half is 20. See? And the radius, this part here is the radius of the large circle, that is 29. And whoa, oh and behold, you've got a right angle triangle here. The hypotenuse is 29, and this side is 20. So you can calculate the remaining side. Is Pythagoras, right? It turns out that the remaining side is 21, and the whole thing is 29. So this part here is 21, and h is therefore 8. And each ring is 1 centimeter long. So if h is 8, it means you've got 8. The question is, how many rings lie in the stack? Beautiful problem. I hope you go and look at it again and translate this problem into nice geometry which you can understand, right? Taking it from the physical situation into this nice geometrical problem. Okay, I'm not doing a problem here because we don't have time for that. That'll take too much of time. But it's this one here. I'm not going to do it today, so it doesn't really matter. If you want, you can try it out and you can ask me. I think I've given you my email address. You can send your solution to me, and then I will check to see whether it's okay, and I will give you a hint on how to solve it if you haven't done it. So that can be regarded as your homework also. Okay, guys, thank you for listening to me. Again, I've abused your time, and I do hope that you learned quite a lot, because today we did a lot of geometry. We had isosceles triangles, we had similar triangles, we had Pythagoras' theorem, we had circles, we had tangent theorem, lots of, nearly every possible theorem that we can get. Okay, so, all right. And in your homework, you'll also